let's think about what might be happen if we had a solution of this carboxylic acid here. We might as well name it just to get some practice. We have 1, 2, 3, 4, 5, 6, 7 carbons. So this is heptan. And then we don't write heptane because this is a carboxylic acid. It is heptanoic acid. Heptanoic acid. So let's see what happens if we have heptanoic acid reacting with, this is 1, 2 carbons, and then it has an OH group. So this is ethanol. Ethanol. That's what the OH group does. It makes this an alcohol. And it's in the presence of a sulfuric acid catalyst. Sulfuric acid catalyst. This is right here is sulfuric acid. One of the stronger acids, sulfuric acid, and I'll actually draw its structure because I always find it frustrating when people just write just the formula here without the actual structure, because the structure actually shows you why it's so acidic. So sulfuric acid, sulfur has 6 valence electrons just like oxygen. So it has a double bond to an oxygen, another double bond to an oxygen, and then it has a single bond to an OH group. And then it has another single bond to an OH group. And notice it has 1, 2, 3, 4, 5, 6 valence electrons. Now the reason why this is such a strong acid is that if either of these oxygens take the electron from this proton, it's actually give away the proton into the solution, there's a ton of resonance structures here. And maybe I'll make a whole video on sulfuric acid just to show you all of the resonance structures. But in general, whenever you see a reaction when they say it's catalyzed by an acid, all you have to do is realize that it's just going to make the surrounding solution a lot more acidic, just a ton more acidic. And we can even, maybe we're in a solution of ethanol, and if we are in a solution of ethanol, it'll just add protons to the ethanol itself. So you can imagine this guy right over here. Let me draw the sulfuric acid a little bit differently. Let me draw these oxygen-hydrogen bonds. So that you have this oxygen, and then it is bonded to a hydrogen there. This is floating around the solution. You have your ethanol. You have your ethanol that looks like this. So 2 carbons and then bonded to an oxygen. And then that oxygen is bonded to a hydrogen. The oxygen has 2 lone pairs just like that. And so this guy really is good at getting rid of its protons. So you have the situation where this electron can be taken back by this oxygen, and then it can actually be given here, and there's all these resonance structures, but it's just very good at taking that electron. And that could happen at the exact same time that one of the ethanols capture the hydrogen proton. At the exact same time that one of these electrons, or this oxygen, captures that hydrogen proton. And if you just look at this part right here, this will just result in, this part alone will just result in a ton of having these protonated ethanols flying around. Actually, let me draw it over here. I want to make sure I'm using my screen real estate properly. So this will result in a ton of these protonated ethanols. So 1, 2 carbons. It has this original hydrogen over here, but now it has 1 electron in that original pair, and then it gave the other electron to this hydrogen. So it gave the other electron to that hydrogen nucleus. It gave that other electron to that hydrogen nucleus. Let me do it in that same color. To that hydrogen nucleus right there. So it took a proton, it gave away an electron, so now it now has a positive charge. And now what was a sulfuric acid now has a negative charge over here. So if I were to draw it, it would now look like this. Plus sulfur, 2 double bonds, 2 oxygens. You still have this OH group. And actually, you could still donate this. It's still acidic. But now this oxygen right now gained an electron. It now has a negative charge. Now, the whole reason I did this is one, to just give you a tangible sense of what sulfuric acid looks like and why it's acidic. But really, you just have to kind of internalize that you're just going to have a bunch of hydrogen protons floating around. They could be attached to an ethanol. If this was a water solution, they could create hydronium. So you have a bunch of hydrogen protons floating around that will catalyze this reaction. They will be used to facilitate the reaction we're going to explore, and then they will be let go. So hopefully, this right here, by having this right here, if I start involving some of these protonated ethanols in our reaction, you won't view that as a huge stretch of the imagination because they would have gotten protonated by the sulfuric acid. Or if I just actually just grab protons in our reaction, that actually might make it a little bit simpler. So let's start with the actual reaction. So let me redraw my heptanoic acid. So I have 1, 2, 3, 4, 5, 6, 7 carbons, double bond to an oxygen, and then we have an OH group right over here. Now, the first step of this reaction, this oxygen right here, we have all of these protons floating around. Very acidic environment. We have sulfuric acid there just giving protons away to the ethanol or to other things. So this guy can grab a proton either directly from sulfuric acid or maybe from one of the protonated ethanols, either one. So we could just draw it like this. He just grabs, I'll just say that he just grabs a hydrogen proton. The hydrogen proton might have had an electron associated with it that would then go back to a sulfuric acid. But just to make things simple, I'll just say grabs a proton from something else. So once he grabs that proton, then it looks like this. So I'll draw my 2, 3, 4, 5, 6, 7 carbons, double bond to an oxygen, single bond to an OH. This oxygen had 2 lone pairs, but now one of the lone pairs is broken up because it gave an electron to this hydrogen proton right over there. Hydrogen proton, it was positively charged. It gained an electron. Now it is neutral. But this oxygen right over here gave away an electron, so it is now positive. Now the next step, we have all of this ethanol floating around. So let me introduce some ethanol. And I'll do this in a different color. So we have this ethanol floating around. And this is 1, 2 carbons. This is our ethanol. You have two electron pairs on that oxygen. And then you could imagine, especially because this is now a good leaving group, you can imagine that this acts as a nucleophile. It would do a nucleophile attack on this carbonyl carbon right here. And so what you could imagine is that this electron attacks or gets given to this carbon right here on the carbonyl. And at the exact same time that this happens, this oxygen is positively charged. It wants an electron. It wants to get neutral again. It's already hogging these electrons. That's why you have a partial positive charge on this carbon. That's why this guy might be attracted to this. We've seen this in SN2 reactions many, 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 many times already. So this electron will be taken up by this top oxygen over there. So after that happens, what does our newly formed molecule look like? Let me just scroll down and have some clear space. So after that, our newly formed molecule will look like this. We have 2, 3, 4, 5, 6, 7 carbons to get to the carbonyl carbon. And now it will have a single bond to that oxygen up there. That oxygen had 1 lone pair already. So it had 1 lone pair already. It had this bond to this hydrogen that it nabbed from the solution, that proton that it nabbed from the solution. And now it has another pair. It had this electron that was participating in a double bond with this carbonyl carbon. But now it took the other side of that bond back. So now it has that electron and the other one that it took from the carbon. So it has 2 lone pairs again. It had a positive charge, but now it took back an electron. Now it is neutral. Now the rest of the molecule, we have this OH group right over here. We have that OH group right over there. And now we have the actual ethanol that has attached itself. So it's no longer ethanol. It's attached itself to this larger molecule. So this oxygen right over here, it still has 1 lone pair, but the other lone pair has been broken up, and it is given an electron to this carbon. It has given an electron to that carbon. It is now bonded to the larger molecule. And then the rest of it, you have these 1, 2 carbons right there. And then you have this hydrogen right over there. Now, the next step of the reaction, remember, we have a bunch of protons floating around. This oxygen right here, and actually I should make it clear, these are all kind of reversible reactions. So I actually shouldn't even draw one-way arrows here. A better thing to do, instead of let me scratch that out, actually let me delete that. A better thing to do, instead of drawing these one-way arrows, is to show that the reaction can actually go in either direction. It's just as likely to go from here to here as it is from there to there. So let me draw that. These are kind of in equilibrium. These are in equilibrium with each other. So you can imagine the next thing that could happen is another oxygen could grab a proton from the medium. And actually, before I do that, let me make sure this guy can lose a proton to the medium. And actually, this guy could take the proton from that guy, but I won't do it like that way. So you could imagine a situation where you have this proton just jumps off. This guy right here has a, oh, and I should have pointed it out. This guy gave away an electron to this carbonyl carbon. So this right here has a positive charge. And in general, the oxygen, very electronegative, it's going to be hogging the electrons of this proton. So it can take them away. It can take them away. So far we gained a proton, and now we can give back a proton. So this electron right here can go back to this oxygen, making it neutral. And the proton can be picked up by anything. It could be picked up by another molecule of heptanoic acid to do this first protonation we saw. It could be picked up by another molecule of ethanol. Let me draw it like that. Let me draw it as getting picked up by another molecule of ethanol. It just gets thrown back in the solution. So this guy gives an electron to the proton, but the end result is the hydrogen leaves, the electron goes back to the oxygen. It now has a neutral charge. So, and once again, these are all reversible reactions, can go in either direction. But we're now over here, and let me redraw my heptanoic acid. 2, 3, 4, 5, 6, 7, single bond now to the oxygen, single bond to this OH, and now we have this bond right over here to this now deprotonated what was ethanol. So we have O, and then we have a 1, 2 carbons just like that, and this guy has a hydrogen attached to it. This guy right over here has a hydrogen, and I won't even bother to draw this protonated ethanol. The protons are flying around everywhere. Now the next step, this guy, this OH group, especially the oxygen in it, he could grab a proton from the surrounding solution. So he's got these two lone pairs. He can grab a proton from one of these protonated ethanols, from the sulfuric acid, or maybe from one of these other kind of intermediate molecules from anywhere. So he could grab, that's the whole point of having this acid catalyst. So he could donate an electron to a proton and then form a bond with it. And so if that, let me do that in a different, I'll keep it in that color. And so if that happened, then the next step in our reaction, and remember, these can all go in either direction. The next step in our reaction will look like this. You would have your 2, 3, 4, 5, 6, 7 carbons, single bond to an oxygen, single bond to an OH, and then you have your bond to this oxygen, which is bound to 2 carbons. 1, 2 carbons, just like that. And this guy on top is bonded to an oxygen. He's got two lone pairs. And this guy over here grabbed a proton. He gave an electron to a hydrogen proton. So now he gave an electron. He had two, but now he gave one of them to this proton. And so he gave it to that hydrogen. That hydrogen is now neutral, gained an electron. This oxygen is now positive because it gave away an electron. It still has this other lone pair over here. Still has this other lone pair. It is now positive, and frankly, it is now a good leaving group. So in the next step, you could have someone else. Remember, other people need protons earlier in this reaction. So this proton might get lost maybe by one of the other ethanol molecules. So let me draw that. Let me do a color I haven't used yet. I'll use orange. So maybe one of the other ethanol molecules or one of the other intermediaries in this whole reaction. So ethanol, I'll just do ethanol because it's easier to draw. It might give an electron to just the nucleus. And then this guy can take the electron back. This guy can take that hydrogen's electron back, give it to this carbon that was the carbonyl carbon several steps ago. And then since he's got that electron, he can then give back this electron to this what was an OH group, but now it got another hydrogen there, so he can then give it back to him. And then the resulting products will look like this. And this is all in equilibrium. We now have 2, 3, 4, 5, 6, 7 carbons. Now this guy has a double bond again. So you have an oxygen right there. It is now a double bond. I'll draw this newly formed double bond in magenta. This guy has left as water. So I can just draw that. So now you have this other OH group that is bonded to this hydrogen over here. He is now left as water. And now you have this other thing over here. You have what was that ethanol group has now attached itself. That ethanol has lost its hydrogen, has attached itself to what was a carboxylic acid. So now it looks like this. It now is bonded to an oxygen and is bonded to 1, 2 carbons, just like that. And this whole reaction that I've showed you is called the esterification. One of those words that I have trouble saying. And this one in particular is called the Fisher esterification. So this is the Fisher, and he won the Nobel Prize in 1902 for generally for his work in organic chemistry. But this is the Fisher esterification. Esterification. And the reason why it's called that is we started with the carboxylic acid, we started with the heptanoic acid, and now we have an ester. And an ester is something that instead of an OH group like you have in a carboxylic acid, you have an OR. You have an oxygen with an actual alkyl group attached to it. And this ester right here, and we'll probably talk more about esters in future videos. This ester right here, just to give you a hint of how to name it, you first start with the group that's attached to this oxygen right here. There are 2 carbons over there, so we'll use ethyl. We'll use ethyl to name that over there. And then we have the rest of this. And we already know that that is 1, 2, 3, 4, 5, 6, 7 carbons, including the carbon in the carbonyl group. And so that is heptan, and you would be tempted to call it heptanoic acid, but it is no longer a carboxylic acid. It is now an ester. So you call it heptanoate. 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 And this is what tells you that you are dealing with an ester. And this tells you what's on the other side of the oxygen in the ester. This is telling you how many carbons you have attached to, I guess you could kind of view it, the carbonyl chain of the actual ester. Anyway, hopefully you found that useful. I just wanted to introduce you to, I guess, a well-known reaction mechanism of creating an ester out of a carboxylic acid.